Okay, so to start the panel, I think listening to this second part of the workshop today, a good starting point to discuss would be the choice of representation. We have heard talks on both sides of the camp. Jitendra says meshes can do anything. We've heard a lot about nerve representations, which are being are very used in the community. Is there a right choice? Is there anything we should be switching to? What do you think is happening with the choice of representation? There's also the implicit representations that are maybe underused currently. Is there anyone that wants to start with this question?
I guess I can start with the hot take I guess I have is that there is no good 3D representation. I think we can keep on talking about it, but it's really test dependent. It depends on what you want to do. And sometimes meshes are great. Sometimes volumetric representations are great. And I don't really think we actually have a specific thing. I think it's better probably to go brainstorming what are the properties that we want from these things. But it's very easy to move from one representation to another. Maybe not all of them in an easily differentiable way. But if you can go back and forth, I mean, you use whatever works, I think is kind of let me start that way.
I think our experience was having worked with meshes. I mean, we are certainly limited to, at least in our case, we started with the sphere. So we were limited to the 0 genus objects, right? And so if we wanted to have things that had holes and things like that, we were not addressing that at all. So I think that's the nice thing that brings, at least the volumetric representations can bring. So that was my sort of take on it, was like the next work that I do would probably be able to generalize more, probably look more at the volumetric representations.
I mean, I think I'm perhaps in the same position as Anju. I don't think it's worth being religious about it, but I do like meshes. Okay, let's take an example. I mean, they work across the board, right? Okay, and so for example, you want to do human stuff. Okay, we have great models like Simple and sort of work such as Anju's on sort of inferring those from images, and there it's very convenient to have this mesh representation, and like the triangles of the mesh mean something. So triangle 57 is my shoulder, okay? It has a clean, simple, easy to explain semantics and all of that, right? So I think there now the genus part, I mean the unchanging topology is an annoyance, but you can deal with it, right? You can just create a point cloud remesh, I mean, so I've been in a couple of projects where we had to deal with this annoying aspect. So the mesh RCNN work with Georgia and Justin had this issue. Right. Then the thing I talked about today had this issue. So it's a bit annoying. I'll concede that, but it can be done. I mean, so and then the nice thing is it's like you may find English as a language is annoying, right? It has these peculiarities of pronunciation, but the fact that so many people in the world use it means that every scientist better learn English, okay, not Esperanto. So
I will say that the mesh is also somewhat restrictive in, like, you don't model hair in, for example, as in the SMPL or most of the face morphable models, right? And if you're going more towards something like digital avatars or something, then you do want that level of detail as well.
Sure, yeah. No, it's the advantage of and disadvantage of a lingua franca. It's like a basic, universally understood representation,
I want to add something that for a lot of this representation, application matters as well. Like, sure, we all like organization, and for that aspect, explicit models is really nice. Everything is well organized. But when you look at some applications, like for example, if you assume a lot of the graphics application, you want to go from a model to an image, and implicit models, they make a lot of assumptions about how they are being rendered. For example, in the case of nerf, a lot of the lightning is already embedded in it, and it's already baked into the nerf. And there are some works, like for example, SNERG, which is some competition to planar trees that Andrew was talking about, that they try to like decouple this sort of rendering part or bake lightning from that implicit model.
I think like that gives a very nice segue to the next question we have on the list, which is how do we like learn to decompose all these complex appearance properties from like in the wild setting, like illumination, specularity, and do we care about these in the context of like shape reconstruction? Anyone want to take the question?
I mean, so again, not the full answer to it, but when we are thinking about handling specularities, etc., in the nerf land, what we are doing is you have these K images, and that is the entirety of what you know. There is no prior about how the world works. There's no prior about structure of shapes, how cars looks, etc. And that definitely makes the problem much harder. Whereas being able to incorporate some prior experience about the world in some way can regularize sort of the solutions you typically infer that, amongst these two solutions, that where the material of the car is varying arbitrarily versus there's a constant and lighting is varying, you prefer the second solution. And somehow these trials have to come in. And I don't think we are doing a very good job at that right now in all of these multi-view reconstruction approaches.
Maybe I wanted to bring the conversation also on another aspect of the 3D reconstruction in the wild. I liked in Jitendra's presentation at the beginning, starting from the baby. I think it's a good way to start thinking about it. And my question is, so in all the works we've seen, there are some form of supervision, some form of priors we rely on. This could be maybe some knowledge of the cameras, maybe some knowledge of the masks, but also it could be something more general, like knowing some reflectance models. And more in general, one could say also just knowing the 3D projection, right? But if you think about babies, then the question is, do they have this kind of prior knowledge that, okay, a point projects on a plane through array and this kind? What do you think would be a reasonable set of priors that one could start from if one really wanted to be inspired by, say, how a baby learns to understand 3D, maybe not in an explicit way, maybe in an implicit way, but in some way make sense of 3D. What are your opinions and your views?
Okay, maybe I'll jump in. So I think that, I mean, in the whole learning business, there is this, we have to separate out various things. There may be some amount of learning which has happened over an evolutionary time scale. So when you are born, at that moment in your genetic code, the basic brain you have has, for example, a kind of spatial structure, right? Your retina has a 2D spatial structure, and there is a mapping which is consistent, which is relating the external world to the image on the retina. Then there is this retinotopic mapping, which goes off from the retina to the visual cortex. So this kind of spatial mapping, where proximity in the image typically means proximity in the scene, is already captured in the hardware, if you will, and it might be there in the basic structure. Now, what cannot be there in the basic structure are the kinds of features which enable you to distinguish a Honda Civic from a Honda Accord, or recognize one individual from another. So that's where the experiences of the child come in. Now, I think that our current models of learning have significant differences with respect to how a baby learns, right? So for example, the experience of a child with objects is with a very few objects, but with a very detailed experience. So it's like the opposite of the ImageNet, where you have like, okay, 1,000 categories with 1,000 examples. Okay, think about the child in the crib, and for the first year or 2 years, she might just be in her home, right? Okay, and playing with some toys, and sees mom, sees dad, sees a milk bottle, Okay, it might be like 100 objects that the child deals with. Even when the child starts to walk, it's in the couple of rooms of the house. So, but on those objects, she may have seen the object from many different points of view, and can even do active experiments, right? Pick up the object, throw it, so forth. So there is little explicit supervision, but there is a lot of this kind of experimentation and this contact with the motor system. So if I take an object and I rotate it with my hands, then I'm getting a cross calibration, because my motor system is telling me something about how much the object has rotated. So in summary, what I'm trying to say is that there is quite a rich supervision that a child's environment has, but it is different from the one that we find very easy in computer vision. But my conjecture is that over time, we are going to be moving in the direction of more natural supervision. And because I think applications such as robotics applications will demand it. I think rich environments like simulators will enable it. Egocentric data will permit it. So I can't prove it, but my vague notion is that I think we'll be moving in the more natural direction.
No other opinions from the rest of the panel?
I think I just want to add to Shang's. He asked a two-part question of how do we do this separating lighting and shape and so on, and whether that's important. So I think I'd just like to comment on the second part of it, which is I think it is important. And I think it's important specifically for augmented reality type applications where you would want to embed 3D objects in real world scenes. And then in that scenario, you do need to be able to separate out the shape and the reflectance properties to be able to relight it properly. And I think these kinds of applications are, from my view of if the industry, I think they're going to come very soon. They're going to be very real. So it's very exciting.
There is a follow-up question from Vidaldi. So you could say that.
I can ask actually, but if you want.
Oh, sure. Go ahead.
Yeah, you were saying about kids becoming expert of a small number of objects, right? So this is something I also thought about a while back. And one of the questions I had back then is, okay, if I learn for 2 years 100 objects, how come I am able then to generalize to everything else? So if I train a machine on 100 objects only, then it's not going to do a very good job on all the rest, right? So it seems that whatever the kid is, the children are learning is highly generalizable, which is not something you would expect of a typical deep network, for example. Not as much anyway.
Yeah, so I think that you're correct. I think our current networks do not squeeze as much information out of the multi-views of 100 objects that than a child does. I think that's correct. And to me, that's like one of the mysteries and one of the great research problems, because I think what we have is a take a canonical example. Okay, so the child has this experience with 100 objects, right, which is very intense. Then the child goes to the zoo, and then the parent says this is a zebra. So now you got like one side view of one zebra. Okay, and that's enough, right?
Yeah, that's right.
After that, you can guess how that zebra looks like from different viewpoints and so on. Okay, I mean, I've done these experiments on my own child when he was 1 and 2 and so forth, and it was amazing. I mean, I tried to, actually take notes and observe this carefully. So I think our systems can't do it. Our current machine learning systems can't do it. And to me, this is probably reflective of the fact that the architecture hasn't captured the 3D inductive bias enough. Because I think 3D is worth building an inductive bias on, because, I mean, the 3D world is the 3D world, and that's just true. It's not like some proposal that let's first detect edges. I mean, that's a kind of thing we have thrown out in the deep learning era. But the 3D-ness of the world, or in fact, the 4D-ness of the world, is something completely to build in as an inductive bias. And what we really need to learn is how do we predict these views in a sort of in a good way. And I think our architectures are not quite there. That's at least my belief.
So maybe to add to that, I mean, we were discussing this in context of 3D and multi-view, but I'm not sure if this is a thing specific to 3D or just an issue with the machine learning tools we use in general, that, kids, even if we are thinking of grasping, they can grasp new objects, even though they have little experience with grasping few. You can navigate in new scenes, even though you've only navigated in a very small number of houses as you're growing up, or new cities, etc. And it's more just that the machine learning tools we use, I think to quote Alyosha, require so much data that the problem becomes like an interpolation problem. And it's sort of a mystery on how we get to more general machine learning tools that get more juice out from very little data. As in, I agree with everything, but I'm not sure it's a very 3D specific issue, or we need just better ways of learning in general.
Yeah, I mean, I agree. I mean, I somehow I think that 3D should be more approachable. Okay, I mean, it's there in other settings, like it may be there in language and this and that, but I feel that, see, I'm making the following analogy. Vision has historically been the part of the brain which has been the most approachable compared to, say, something like language. I mean, motor control is also approachable, okay, because we kind of understand the first few stages of processing in the visual pathway quite well. So I would conjecture that the area where we might be able to tackle this problem most successfully, or what might be the most, plausible place to attack first might be vision and 3D, though it may be a universal issue.
Yeah, I'd like to add, I agree with all of these directions. I'd like to add 2 points. One is that I think it's also like a matter of the training paradigm in which do things, where there's like a fixed set of data sets. And then from then on, we close our eyes and like never look at the world again. And I think it needs to be like, you need to have some kind of feedback system where, in reality, you actually get multiple views. And so you update your model and like you continually learn. And I think that kind of direction would be really cool to see in 3D. But another thing is that even if you get to see the 100 objects, I really want to emphasize that the lighting in the environment is very complex in the real world. And so the baby is looking at 100 objects maybe, but they get to look at it in like all sorts of lighting, from like the morning, night to like fluorescent and all of these things. And it's actually quite diverse. I think it's a really good learning signal. And another thing that I feel is that maybe it doesn't, I can't really express it, but I feel like the reusable pieces, 3D priors, are actually going to be small pieces. And for those things, maybe that's a lot of signal. Either way, I still think you need some kind of online learning, but I'm saying it's a lot for the baby get to see a lot.
Maybe to add a little bit more to this point. So I think that the work we're referring to is the one of Linda Smith, right? Where basically, and she notices that from all these videos that basically the babies learn mostly from very few objects. Then the question is, why is it better to learn from very few, but very, very much in detail, like with very high accuracy so that they can recognize a bottle, although it's mostly occluded, rather than from a variety of objects, right? That's, I think, a little bit maybe one point of the question. Why does the first one generalize seem to be favored by evolution? Maybe.
Well, we may not have a choice, right? I mean, see, today, yes, we can go to a, to a Walmart and have thousands of objects. But imagine any animal's ecological niche. They're in like some part of space. They're in their forest or in their tree or whatever. And in general, it's your life is local, right? Even humans as hunter-gatherers, they would be in like some place, or if they had lived in a village, they were, I mean, the idea that we can roam around the globe, I mean, this is like a very 20th century thing, right? So you, in general, had a very local context, a local cultural context, a local context of vegetation, local context of flora and fauna. So I don't think there was a choice. Now, why is it that computer vision has found it easy to use knowledge like this ImageNet thing, and yeah, I mean, Shubham referred to this line that maybe all we are doing is interpolation. In fact, there is some amazing work from some machine learning people, Ben Recht and co, which show that networks can memorize basically anything. So you could take a set of 1,000 digits, arbitrarily label, I mean, and just give them random labels. So instead of 0, 1 to 9, you can label a 6, a 3, or whatever, any number, totally by random assignment. You label all those 1,000 digits, and now you can train your network, and it will, the neural network, you can get the training loss to go to 0. So it will overfit to this data set. So there is no generalization here. So all that it is doing is memorizing those 1,000 examples. So our networks have amazing, they memorize this, which is what we are exploiting, which must mean that there is some hidden secret sauce somewhere, which we should be able to incorporate in our network, and then you'll win.
Maybe just to add to that, it's true that you can force a network to learn anything you like, but it doesn't mean that the network really likes it, right? So it would typically actually not do that, probably, right? So otherwise nothing would work. So you can make it do it. You can make it do that, but you really need to press it, I think. It's a bit like when we did a deep image prior, which we could fit random noise with a generator network, but that was very hard. So it was much easier to fit a natural image. So I think, it's true that the network can do anything, but not necessarily something that is not necessarily something which would be preferred if another solution could be found.
No, fair enough. Look, I think that the search for network architectures is not over yet. Look, for so many years, we just went with ConvNets, right? Okay. There were people who didn't like ConvNets, like Jeff Hinton, right? He wants capsules because he thinks that the operation of pooling is losing some vital information. Fine. Okay. Those were difficult to make work. Okay. Then we got to transformers, like maybe 3 years ago or something in language, and then last year in vision. And this is a different architecture, right? It's completely ignoring spatial invariance of these patches. It's doing these long range connections, and we can use it for all our things. So why should we assume? So I'm essentially saying that earlier I really think we might have next year, we might have something quite new and revolutionary. So the space of architectures is, I don't think, exhaustive. And they might, like, to me, like transformer, like ConNet seem to capture low-level structure, but at higher level, they didn't seem to make sense. And it seems to me that transformers do something more natural for more high-level structure, but why nothing captures the 3D nature of the world? Who knows? I mean, I think we should not. I think people will come up with new things. Who knows? So I'm an optimist.
Good.
I want to make a connection back to the question I asked earlier. Like, oftentimes when we want to predict shape, like 3D shapes, like throw in the 2D image into CNN and predict all the vertices in XYZ coordinates, which are like far too different from the input space, which are pixels. And it completely ignores the 3D projection and this encoding process. I do really wonder, like, if there's any way of incorporating these knowledge about 3D or other like properties in this prediction process.
You mean more than just? I mean, we are doing it, right, with the cameras and perspective projection and all the rest. You mean more than that? I mean, so obviously the brain knows about triangulation, right?
The prediction model, like, you cannot just like throw in a 2D image into a CNN and predict everything, right? Or do you think like that's not a problem?
Yeah, no. I mean, my belief is that the reason why that 2D image evokes a 3D is that you have learned across modalities. So here is this object in front of me, right? Okay, so right now I'm seeing it with two eyes. So it has got a certain pattern of disparity associated with it. Okay, now what I do is I shut one eye. Okay, but I have this mental association of this 2D pattern of pixels with a certain pattern of disparities. That pattern of disparities evokes a certain depth. So therefore, just the pixels evokes that pattern of depth. So A is associated with B, and then B is associated with C, and then A goes with C. Something like that. I think that's a fairly reasonable thing to assume in a learning system, right? And it's more than that. It's also because, I mean, humans are also very adaptable. That's one of the impressive things. So there is this classic experiments where you have your two eyes, and now in front of one of your eyes, I'll put a prism. So what happens is all the rays are like deviated by 10 degrees. Okay. So now if I try to pick up an object, I'm in trouble, right? Because my stereo system has got messed up. So I keep trying. Okay. After 10 minutes, I will basically succeed in grasping. And now my brain has quickly got rewired. So this hand-eye coordination has been adaptively reconfigured in like 10 minutes of action, but it was active interaction. So there seem to be a whole lot of these features where there is this geometry built in, these constraints built in, and yet they seem to be very, very adaptable and plastic and so forth.
Yeah, I think like that totally makes sense.
So I think another point that we have slightly touched on that would be interesting to talk about that follows out of the previous discussion is what kind of data should we be working on? So we now talked about that we should be learning like the children. So do we strap cameras to babies and record videos and train on that? Or do we go towards the interaction aspect and use simulators to actually learn from the interaction with objects? Or should we just continue what we're doing now and use, I don't know, image and video data sets across hundreds or thousands of categories and try to generalize from there?
I might be a bit biased, but I think it really depends on your application. Like if you are trying to make AGI from babies to young adults, sure, you should put a camera on a baby, don't ask Google to do it. It has a lot of privacy issues for the babies. But if you, for example, care about product that people sell on the web, then that's a different application and it would require different data. So if you ask different person, you might get different answers for your question.
Okay. I don't mind what you use so long as you stop using ShapeNet. I think ShapeNet should be retired. It's outlived its usefulness. But I think all the answers you suggested are good. Like I like simulators. I like egocentric data. I think multiple views is the most natural. Okay. So anything, and I think we can get some, I mean, from Berkeley, we are releasing this something we did in collaboration with Amazon, which is like lots of images of and CAD models of Amazon products. So that will be like more like CAD models. So honestly, anything you can get. We are really quite limited by data. I think the 3D space, we are starving for data. I think why is 3D not why is the field not bigger than what it is? I think Shalini referred to the fact that like upcoming applications like AR, VR will really emphasize the need for 3D. Okay, but why are the number of papers in this area and the progress in this area would really benefit from having tons of data? And for 5 years, we wrote papers just on ShapeNet. Okay, between like 2015 to 2020, it was all ShapeNet. Okay, well, okay, fine, retire it. You know.
I completely agree, and I think that we need 3D, like videos, maybe multi-view videos, but I think we actually also need good 3D data, not like with holes and good quality, which can capture a lot of the photogrammetry, scans and things like that. I think that will really help to progress the field further, because at the end of the day, we're estimating all this 3D, but then how good are we doing, right? Like, are they good enough for a real world application? Like, is there detail in it? We don't know. And the only way we can know how well we're doing is if we have some good ground truth to compare against. I think there was this spurt when we had Connect and there was a lot of 3D data of research in 3D, but then now that's kind of all sort of not as, that's not as prominent anymore.
Yeah, I want to raise a point though that I think it should be images in the wild, and I think that's very important. And the moment you go to in the wild, it's much harder to get the training data, but we'll always figure out how to do the evaluation. Like Shubham was proposing one way. Yeah, I think it's very important that not only does it has to be data, not ShapeNet, but ShapeNet has multiple things, right? It's synthetic, but also the problem is that things in the world don't exist in a vacuum of white background, and so we can't just go back to a rolling object on a thing with a rolling table with a green screen background. That's also not so great either, I think.
Yeah, I mean, maybe we might hit lucky, right? So all these new generations of phones, they have quite, they have the ability to capture 3D. True. So suppose we get into the setup where, look, think about the basic setup for images. Back in the late 1990s, early 2000s, what happened was, okay, everybody started to own a phone with a camera. Then they started to upload those pictures. And then in those days, we didn't care so much about privacy and so forth. So people started downloading those pictures and making data sets, right? And that's the basis of data sets like ImageNet and so forth, right? Okay. Now imagine that if everybody was uploading 3D pictures, okay, at the same rate at which people were doing for 2D pictures, maybe we would find a way to exploit it. Now, I think the difference is the sort of the legal and socio-cultural context has changed from 10 years ago. So I think the way people could just download images and annotate them and make a data set, I think that era is gone in my view. Okay, so we'll need to be more careful and particular. But that could be the source ultimately. That the beauty of that is that it's truly crowdsourced. You get huge variety, because if I collect any one person collects data, it lands up being from their own sort of niche, right? Whereas if everybody is collecting, if you've got like 1 billion people in the world uploading data, it's going to be much more varied.
Yeah, we need a framework to buy this data though, or to commission this data. So we have done this in the Code3D data sets where we paid people to capture images of objects. And of course, once people have these 3D phones in their hands, we could have just asked them to capture 3D videos or 3D pictures.
Yeah.
So, but we can get probably hundreds of thousands of images, maybe 1 million, but not 1 billion like that.
Yeah, but I think that's a promising direction, right? Yeah.
It's interesting, Andrew, that you say that in the real world there are not the white background scenarios, but basically all the methods we heard about today, or that are state of the art, need mask supervision, which basically directly translates into having the white background during training. So that's one of the very interesting things that basically is consistent across all methods, that we need this supervision of the shape of the object, at least in 2D.
But the issue with relying on user-generated content in these instances, it creates two bias. One is you're assuming that users are taking them with their phone, and then you're limited to the location where the phone is and how the phone is viewing the object and so on. For example, think under the table. Like if I ask any one of you what does under a dining table looks like, you all know what it looks like. But if you rely on the internet images to understand or learn that might not exist. Number two, you also would be relying on countries where people have a lot of phones, and two, they have a really good internet access to upload these phones. For example, think a lot of countries on the planet, they don't have this sort of infra. And also three, like if you are trying to, like, for example, learn how a baby learns an object and grasp an object, I don't think a baby would take out of her phone and take a picture at the same time. So you're learning what an adult person views the environment, and you're learning that.
Yeah, no, I think those are also valid points. But going back to Christian's point about the semantic segmentation mask, what was I going to say? I actually think this is okay. Or like, actually the interesting point is actually we go back to Jitendra's like 3 R's, right? Like recognition, reconstruction, and reorganization. I think the catch, is that once we have a lot more diverse data, we would be doing the clustering or like identification of the objects or the objectness. All of those things could also stem from 3D. Like all of this top-down and bottom-up reasoning should be done together. And like, maybe we can start thinking about that. That's kind of nice. Second, I think like, not only is the white background really bad, but like, it's not about really segmentation, but also the fact that like, they're going to be clutter, which means the semantic segmentation is going to be it's going to be modal, and that like, we want to, that's also like an important thing to do. Yeah. And if we're going on a wish list of like what kind of data sets to get, actually, I want to point out that like, I really like lighting, like different lighting gives you really, really important information. So if you're actually going around and collecting data, it would be super cool if you could get like a similar data under slightly different, lighting, maybe in like the version 2 Andrea wish list.
No, that's an interesting idea. I guess you just need to be careful that people don't kill themselves because they switch off the lights or something like that. Actually, yeah. So, yeah. You never know. Yeah, to be a bit careful not to ask people to do dangerous things. But yeah, sure. Maybe just put a light or something. Yeah. Or use the flash on the phone. Actually, that could be easy.
That could be easy. It would be nice if morning, night.
Yeah.
So, yeah.
I mean, the thing I always worry about with neural networks is that they overfit quite easily. So I mean, we are interested in the 3D part, but this lighting, if we just don't have variety there, we could end up fooling ourselves in some terrible way.
Okay, then I think we are out of time if there's no more comments right now. Then I would like to thank all the speakers of today. It was a very interesting workshop. I think everybody learned a lot. Thanks for joining the talks and the panel session. And yeah, I hope you have a great evening, morning, day, night, wherever you are, and see you throughout the conference.
And good ICCV to everyone. Bye-bye.
Bye.
Thanks, everyone.
Thanks for organizing.
Bye-bye.